in a similar fashion to things that Argonne does already for the Department of Energy or so. The US Department of Transportation is not as computing intensive as you might think or so. So what they consider their biggest supercomputer, which is ours, is actually a 512 core machine. So it's sizable, right? But it is actually something where we can easily meet right now the demand of the transportation community for high performance computing. At least, let's say, for the next year or two, and then maybe get a replacement machine that has a higher capacity or so. There are all kinds of things that we can do, and traditionally in the Department of Energy, we have done simulations for pretty much everything on computers. When it comes to the Department of Transportation, they rely a lot on experiments, actually costly experiments at this time. So a move to this modern technology, like has been done in the Department of Energy, makes a lot of sense to them, but it takes a long time to change the infrastructure and the way of thinking and the rules and liability bases. I mean, the Department of Transportation is organized very differently from the Department of Energy. I mean, for one thing, you don't have an individual state Department of Energy in every one of the 50 states, right? So there's a lot of difference in the way at Argonne that we have been thinking about how to do big projects like this. So the kinds of things that we would be doing are bridge hydraulics and bridge structural analysis using computational, structural computational mechanics and things like that. We also do a lot of transportation simulations, everything that requires supercomputers, and we provide the center as a service to the transportation research community. Here's a short description of the computer itself. That is mostly important when we try to advertise this to the research community because it's a free resource. So people who are doing transportation research can apply for access to the machine. And the emphasis is on running really, really large cases that make really use of many, many of the machines in parallel. We are located not at Argonne, so that's a little unusual. We're a group of, well, if you have staff members, between 15 and 20, if you count all the subcontractors and students, might be 25, something like that. So it's a sizable group, but we're running our own operations out at the DuPage Airport, right north of Fermi. Besides the computer that we provide to the community, we also have a great visualization center that can be used for training, for collaboration, remote collaboration, and things like that. And we have become so used to it that we basically can bring up a conference with a large group of people, like hundreds of people, just in a few minutes if that's necessary, which is great because most of the people we work with are really distributed across the US. We don't have so many local users. This is a slide that shows a little bit about the Collaboratory, as it was called recently. This comes actually from the National Center for Supercomputing Applications. They were operating this visualization center as an outlet to show how modern visualization technologies can be applied in the industry. That's where that comes from. And they lost funding about August of last year, and then we had a great arrangement where the University of Illinois actually donated all the equipment to us, and we took over the personnel, so that increased our capabilities quite significantly. So we have great training facilities. This is also a great place to have meetings and bring people together. We are also sitting on all the high-speed networks, which is really important because access to the supercomputer is basically exclusively a remote access mechanism. So with the ESNet and the DOE labs and things like that, we have very fast access within the traditional community. But it turns out that all the US DOT research centers and the other local researchers that work with us, that 95% of them roughly sit on fairly sizable networks, so they can access the resources really well. Same thing is true for the universities, of course. Besides the provision of the actual computer to the community, we have, let's say, 4 major areas where we do our own research. That comes from funding from the US Department of Transportation, but a lot of funding also comes from the state, from the city, Illinois Terrorism Task Force, and other agencies like that. The 4 areas that we concentrate on are the traffic modeling and the simulation. That's more my specialty and my group's specialty. Then we have also data visualization, because with the amounts of data we produce with the supercomputer, it's very important that we have really advanced ways of looking at this for analysis and also to show our results to others, of course. computational fluid dynamics is something where you need a lot of CPU power for really complex things. We go into each of these areas with a slide in just a minute or so. The last thing is computational structural mechanics. So this is basically the analysis of bridges and looking at the deformations exposed in wind and so on with very, very detailed finite element methods. This is the kind of transportation simulation that we are running. We are using a code named Transims, which has been developed over the last 10 years or so by the US Department of Transportation. The code has actually been dramatically modernized in the last 3 years or so. And the specialty is that it can cover extremely large areas and does not rely on the traditional concepts of capacities and macroscopic parameters. Rather, you look at each individual, not even every car, every individual traveler and all their movements across the network. So you look how the cars have to avoid each other, pass each other, stop in front of traffic signals, all those kinds of details. But you also look at all the different transit options, and everything is basically modeled as individual vehicles, travelers, and things like that. And it can be even activity-driven, so that you don't define what trips take place from a certain spot to a certain spot, but the activities by which those trips are necessitated. That requires extremely detailed route networks, and you can imagine that looking at the results, but also to look at the inner workings of the software, you need the visualization to just make sense of that amount of data. So we did a lot of video methodologies to actually turn this into little videos. I cannot show them here because that's not on my computer. Now, the capabilities of the software are very promising because nothing breaks down just because you don't have a normal day scenario anymore. It doesn't mean that we can predict chaos by any means or so, but we can go close to accident scenarios or evacuation scenarios for a city like Chicago, and that's one of our big projects, and look at the development of specific scenarios that are being used and planned right now by the emergency response planners. For example, busing people from the affected area to central collection points, taking them out. Since we know exactly how much time it takes for every person to enter a bus, how the bus moves in traffic, how it might have reserved lanes, how many buses might be making it there, and we calculate also the movement of the individual people from their building out on the street, how they walk along the street, and so on. We can basically live with a fairly inaccurate system and still make reasonable assumptions about the delays that every person encounters on their trip. Right? So this is the kind of thing that we're working on. In initial phase has actually just been finished, where we showed the proof of concept, and in a few months we basically move on with a larger phase 2 for this. Another thing is then the computational fluid dynamics. So that's not my area of expertise, but there are several different things that are important for the transportation community to look at. That might not be as interesting for you because it's not so much energy related, but computational fluid dynamics can be used to look at the scouring of bridges in flood conditions and things like that. So that might not be a direct link to the kind of work that we're talking about here. But we have, for example, the dispersion of toxic and radiologic biological agents in urban environments. So you look at emergency situations, unusual contamination patterns and things like that. And together with the traffic analysis, you can then conclude the overall exposure to agents, radiation and things like that. Another thing that you can look at is the dynamic forces of a flow against a bridge deck. So what you see here is a bridge deck, and you cut right through it, and you see the rafters underneath there and the side walls on the side. And this is a bridge on the Lake Pontchartrain during the flooding in New Orleans. So what you see is basically the water forces that are put on the bridge and might displace it and might break it. So they do this kind of analysis with the computational fluid dynamics. Structural mechanics, there's a whole bunch of interesting applications. So crash worthiness is, of course, one that you replace the expensive crash tests that they do these days. But it's also not just cars, because that's done by the manufacturers, but of route hardware, like bumpers and all these kinds of security, safety devices that are built in. there has been work that has been done to understand the interactions of colliding trains, for example. The FFA was interested in crashworthiness of aircraft and things like that. We had one calculation that was not performed by us, but from a partner institute that uses our computers about the structural mechanics in the brain during an impact. So you run many, many different brain simulations and can conclude then statistically what level of damage is caused by different kinds of impacts. The advantage is that with a cluster like ours, you can run much higher fidelity models. I think we have here, the Emerson bridge. This is a bridge where half of the bridge used to be modeled with about 500,000 finite elements or so. Then it would take, on a 32 CPU cluster, several months or so to come to the solution of this. Now on our cluster, you can run it on 1 million finite element grid and get the results in a couple of weeks or something like that. So it makes a big difference whether you can run this on 100 or 30 computers. And that's the end of the presentation. So if you have any questions. Sure. Yeah, I mean, the beauty and why we're using transims, because it's an experimental code. They have used it in the White House area to look at the traffic flow under different assumptions of tunnels being built. There's this congestion around the White House since the roads are all closed. And there are actually 6 different proposals about tunnels and things like that. So as a result, they determined that 5 of these really don't improve the traffic flow at all. I mean, the congestion being experienced. The power of transims is that you follow individual cars, vehicles around, which means you can plug in behavior models for individuals, you can track their every movement. And one of the things we talked about at lunch, and we'll probably talk about that then at 3 o'clock in the summary, that there are all kinds of options to look, for example, at the system impact of battery-operated vehicles, right? I mean, where would you, for example, place refueling stations? Well, for batteries, that might not even actually be the urgent thing, but people might behave differently driving into congested areas if they have a gasoline car where you can have a little container and refill your car in worst case, right? Versus going there with a car that's operated by a battery that you cannot exchange on the road. Mm-hmm. Yeah, I mean, that's one of the nice things that we do. We have lots and lots of students actually work out at track with us. I try to damage their brain differently, right? I just sit them in front of a computer for boring things like network editing. They usually turn out to be much more intelligent than that and move on to much more interesting things.